The finding began its journey from an anomaly to a potential new piece in the cosmological puzzle, a piece that suggested a greater diversity in the early universe's developmental pathways than previously appreciated. It was a testament to Hubble's enduring power, even in an era of newer, larger telescopes. Its unique combination of sharpness, sensitivity in the near-infrared, and now its long baseline of archival data allowed it to make discoveries that fundamentally questioned the timeline of cosmic dawn. The data that arrived before the vanishment had done its job. It had provoked a new line of inquiry. Yet, for Dr. Vance, a personal and philosophical conclusion was forming, one that went beyond the academic impact. Sitting in her office after the publication, she considered the full arc of the story. It began with a routine observation, one of thousands. It was almost lost to a mechanical failure, becoming the data before the vanishment. It was saved by a decade-old archival note, a forgotten whisper that gave context to the final shout. It was validated by an entirely different telescope on a different continent, seeing a different physical component of the same object. And it would, she knew, eventually be followed up by the James Webb Space Telescope, which would, with its piercing infrared gaze, finally obtain the definitive spectrum, measure the exact redshift, and map the gas dynamics in detail. This was not a single eureka moment, but a chain of connected insights across time, technology, and human collaboration. The scientific process was not a flashlight revealing truth in an instant, but a slow dawn, where different instruments, like sensors of different wavelengths, gradually built up a complete picture as the night receded. Hubble's pre-failure data was a crucial, poignant data point in that dawn. It was a glimpse that was both an ending and a beginning, an ending of a period of Hubble's operational certainty, and a beginning of a new mystery that would be passed on to its successor. The telescope, in its moment of silent crisis, had transmitted a final, deep message about the universe's capacity for surprise, about the existence of places where time itself seemed to flow differently in the frantic first moments of creation. This message, decoded over months of painstaking work, was ultimately a lesson in humility. The cosmos was more inventive, more varied, and more eager to evolve than our smoothest models could capture. The beautiful, monolithic narrative of hierarchical structure formation now had a fascinating, intricate subplot written in the faint glow of ionized hydrogen and the cold whisper of primordial dust, a subplot first spotted by an aging telescope staring into the abyss, faithfully sending home what it saw before the data stream went silent, ensuring that its last clear vision would become a new question for the ages. In the months following the paper's publication, the story of the anomalous glow entered a new phase, one of quiet assimilation into the broader scientific consciousness. It was cited in review articles on high redshift galaxies, featured in conference presentations on reionization, and served as a key motivation for several observing proposals submitted to the James Webb Space Telescope. Its legacy, however, was cemented by an unexpected development from within the Hubble archive itself. An amateur data sleuth, a retired radio astronomer with a passion for algorithmic pattern recognition, was running a self-devised machine learning routine on public Hubble data, searching for subtle, low-surface brightness features that might have been missed by standard pipelines. His algorithm, trained to ignore obvious galaxies and artifacts, flagged dozens of curious regions across various deep fields. Among them, with a high confidence score, was Hubble's pre-failure glow. But the algorithm also flagged 4 other similar features in other shallower Hubble fields, extended, faint halos of emission that had been buried in the noise, dismissed as background fluctuations or scattered light. They were not as bright or as statistically significant as the primary discovery, but they shared its morphological character: diffuse, asymmetric, and associated with a handful of faint point sources. When the amateur shared his findings with the professional community, It triggered a systematic reanalysis. The result was not a population of identical behemoths, but a spectrum of such objects, with the original being the brightest and most extreme example. This was a critical turn. A single anomaly could be a statistical fluke, a cosmic oddity. A handful of similar objects, even fainter and rarer, suggested a new class of astronomical object, a previously unseen phase in the life cycle of the earliest structures. They were not protoclusters in the mature sense, but perhaps protocluster cores, or ionized bubbles in formation, the bright central engines where star formation was most violently concentrated, shining like lighthouses through the neutral hydrogen fog. The discovery from the vanishment data had provided the template, the archetype that allowed astronomers to know what to look for and where to look in the vast photographic plate of Hubble's legacy. This archival renaissance underscored a profound truth about modern astronomy. The data often holds secrets it was not originally asked to tell. Hubble's decades of observations constitute a frozen library of cosmic history, and each new analytical technique, each increase in computational power, allows scientists to read that library with new eyes, extracting stories from the same photons that arrived years or decades prior. The pre-failure data was now part of this ever-growing, ever-interpreted library. Its significance was no longer just in the specific scientific finding about early structure, but in its role as a catalyst for a new way of mining the past. It demonstrated that the most interesting signal might not be the brightest galaxy, but the faintest haze connecting them, not the soloist, but the chord. This shifted the philosophical framework from discovery of discrete objects to the mapping of diffuse processes, from cataloging islands of light to charting the luminous currents that flow between them. The universe, as seen through this lens, was less a collection of points and more a complex, glowing web of interactions, and Hubble's final deep stare had captured a particularly ancient and pristine segment of that web, a segment where the weaving had begun with astonishing speed. Meanwhile, on a practical level, the director's discretionary time proposal for Hubble's spectroscopic follow-up was approved. The telescope, now operating steadily on its reconfigured gyro system, was scheduled to revisit the field. The plan was to use the Space Telescope Imaging Spectrograph, STIS, and the Cosmic Origin Spectrograph, COS, in a coordinated ultra-deep campaign to try and secure the elusive definitive spectrum. The goal was to spread the faint light of the glow into its constituent colors, to find the exact wavelength where the Lyman-alpha line had been redshifted, and from that, calculate the precise distance. It would be a heroic effort, requiring dozens of orbits of patient integration, pushing Hubble's spectroscopic capabilities to their absolute limit. The observation was scheduled for a time when the field was optimally positioned, a slot carved out of the crowded timeline. As the date approached, a sense of poetic closure settled over Dr. Vance's team. The telescope that had first seen the anomaly, in its last clear moment before a stumble, was now being asked to turn back and look again, to explain its own tantalizing glimpse. It was a conversation across time, between the Hubble of then and the Hubble of now, with the same hardware attempting to answer a question it had itself raised. This recursive loop observation, analysis, question, follow-up observation is the fundamental engine of science. But here it felt particularly intimate, a dialogue with a machine that had become a collaborator. The observations were executed over 3 weeks in a series of lengthy, uninterrupted orbits. The data downlinked, clean and full, with no safing events, no transmission anomalies. The team processed it with a nervous urgency. The spectroscopic extraction was a meticulous task of summing the signal over the exact spatial region of the glow, subtracting the complex background of sky glow and instrumental noise, and searching for a spectral feature. And then they saw it. Not a sharp, clear emission line, but a broad, asymmetric bump in the spectrum. a red-tailed excess of photons centered at a specific wavelength. It was the Lyman-alpha line, but it was heavily processed by its journey through the intergalactic medium. The neutral hydrogen atoms that still filled the universe at that epoch absorbed the blueward side of the line, chopping it off and leaving only the redward side to propagate, resulting in a characteristic asymmetric profile. The precise shape of the bump and its central wavelength confirmed the photometric redshift estimate beyond a reasonable doubt. Z equals 11.9. The light had been traveling for 13.25 billion years. The universe was only 380 million years old when that light was emitted. This spectroscopic confirmation was the final piece of forensic evidence. The anomaly was real, its distance was locked in, and its place in cosmic history was secure. It was one of the earliest structured objects ever identified, a bustling region of star formation and gas dynamics from a time when the cosmos was less than 3% of its current age. Hubble had not only discovered it with its imaging camera, but had now, with a monumental effort, used its other instruments to definitively certify its own discovery. The circle was closed. The data that had arrived before the vanishment was no longer just an intriguing hint. It was a confirmed waypoint in the timeline of the universe, a benchmark for all future theories of how the first colossal structures began to assemble in the primordial dark. With the spectroscopic confirmation secured, the narrative of Hubble's final pre-failure glimpse evolved from a mystery to a milestone. It became a fixed point in the expanding frontier of high redshift astronomy, a luminous signpost at the very edge of the observable universe. Yet, in science, every answered question births a new generation of inquiries, more detailed and more profound. The confirmed existence of this massive, rapidly evolving structure at Zeta-12 forced a fundamental re-examination of the initial conditions of the cosmos. The seeds for such an early collapse are sown in the first trillionth of a second after the Big Bang, during the period of cosmic inflation, when quantum fluctuations were stretched to macroscopic scales, imprinting the primordial power spectrum, the blueprint for all future structure. The extreme overdensity implied by Hubble's protocluster suggested that the inflation field, whatever its nature, might have produced fluctuations with more power on very small scales than our best models, derived from the cosmic microwave background, had indicated. The CMB gives us a picture of the universe at 380,000 years old, showing the density variations on large scales. It is a somewhat blurred image, and the details of the smallest scale fluctuations are less constrained. Hubble's discovery was like finding a colossal mountain on a landscape where our maps had predicted only gentle hills. It hinted that our mapping of the inflationary terrain was incomplete, that there might have been localized peaks in the quantum foam that spawned correspondingly dramatic overdensities in matter. This connected the infinitesimal physics of the quantum realm to the grand architecture of the cosmos in a direct and startling way, suggesting that the universe's largest structures could be traced back to rare, intense wrinkles in the fabric of space-time itself, wrinkles that Hubble had managed to glimpse in their first luminous awakening. This connection to inflation theory brought the finding to the attention of a different community, the cosmologists who model the first moments. Papers began to appear exploring peak theory in the context of the primordial power spectrum, calculating the expected abundance of such extreme overdensities and what they could tell us about the shape of the inflationary potential. The Hubble protocluster, now often referred to by its catalog designation as the Vance overdensity within specialist circles, became a datum in cosmological parameter fits. It was a nuisance to some elegant models, a welcome challenge to others, but to all, it was a reality that had to be accounted for. This was the ultimate destiny of a deep field observation: to cease being merely an image and to become a number, a constraint in an equation, a small but stubborn weight on the scales of cosmological theory. The quiet tension the finding introduced was not of dramatic revolution, but of subtle, persistent adjustment, a gentle pressure on the theoretical edifice to make room for a greater diversity of beginnings. It spoke of a cosmos that was not monotonically uniform in its initial state, but one that might have contained dramatic regional variations from the very start, a universe with a more textured and interesting infancy than the perfectly smooth baby picture of the CMB alone would suggest. While theorists wrestled with origins, observers looked to the future. The confirmed redshift made the Vance overdensity a prime bullseye target for the James Webb Space Telescope. In its first cycle of deep observations, Webb turned its golden mirror toward this coordinate, employing both its cameras and its powerful spectrographs, not just to look at the overdensity, but to look into it. Where Hubble saw a diffuse glow and a few point sources, Webb's exquisite infrared resolution began to dissect the region into a swarm of dozens of distinct, tiny galaxies, the building blocks of the protocluster. Its spectrographs did not just confirm the redshift of the overall haze, they began to measure the velocities of individual galaxies within it, revealing that they were not a static cloud, but a dynamic, collapsing swarm, gravitationally bound and falling together. Webb's data showed the cold gas reservoirs in stunning detail, confirming ALMA's dusty detection and mapping the flow of gas along the filamentary structures Hubble had only hinted at. The story grew richer, more complex, and more definitive. Webb was writing the next chapter, but it was a chapter whose first sentence had been penned by Hubble in its moment of silent crisis. This handoff from one great observatory to the next was a poignant moment in the history of astronomy. It was a demonstration that exploration is a continuum, that each telescope builds on the legacy of its predecessors, and that even an aging explorer, in its final years of service, can point the way for its more powerful successor to places of profound importance. Hubble's last deep stare had effectively created a scientific to-do list for Webb, a list that Webb was now eagerly checking off, revealing a vibrant, chaotic construction site at the edge of time. In this new light, the original Hubble data took on a different character. It was no longer the final word, but the first draft. Scientists began to perform a kind of forensic reenactment, using Webb's detailed map to go back and see if they could find hints of the individual galaxies in Hubble's pixels. With the knowledge of exactly where to look, they could perform sophisticated image stacking and deconvolution, and faintly, like bringing a blurry photograph into focus, some of the brighter knots in Webb's image could be marginally discerned in Hubble's. This retroactive discovery was a testament to Hubble's latent potential and to the ingenuity of data analysis. It showed that the information had been there all along, hidden in the noise, waiting for the key to decode it. That key was the deeper, sharper vision of Webb. This iterative process, Hubble's detection, Webb's resolution, and then the reinterpretation of Hubble's data with Webb's guidance, is the scientific method in its purest and most collaborative form, a dialogue across wavelengths, across technological generations, and across the vast distance to the target itself. The data that arrived before the vanishment was the opening line in that dialogue, a line that would be quoted and analyzed for decades to come. For Dr. Elara Vance, the culmination of this years-long journey brought a quiet, reflective satisfaction. The finding was no longer hers or her team's. It had been absorbed into the canon, a small but permanent part of humanity's map of the universe. She often thought of the photons that had created the image. They had been emitted by massive, short-lived stars in that frantic early cluster. They had traveled for over 13 billion years, through the expanding universe, through the thinning gas of intergalactic space, unimpeded until the final millisecond of their journey. When they encountered a polished mirror and a set of silicon detectors orbiting a pale blue planet, they had been converted into electrons, then into bits, then radioed to Earth, processed, archived, almost lost, recovered, analyzed, debated, and finally understood. It was an epic journey for a particle of light, and an epic journey for the humans who traced its path backward. The Hubble Space Telescope was the instrument that made that tracing possible. Its temporary blindness, its vanishment, had ironically illuminated the preciousness and the potential of every photon it collected. The story of what Hubble saw before the data vanished was, in the end, a story about attention, about the value of looking deeply and patiently at one small piece of the sky, and about the enduring human quest to find our place in a story that began long before us, in a cluster of stars so early that their light is only now arriving, a story that continues to unfold with every new gaze we turn toward the cosmos. The assimilation of the Vance-over density into the cosmological framework represented a closing of one loop, but in the vast and interconnected web of cosmic inquiry, it served to open others, casting long shadows of implication across adjacent fields of study. One such shadow fell upon the enigmatic nature of dark matter itself. The sheer precocity of the structure's formation, its early collapse and rapid star formation, provided an unprecedented laboratory to test the properties of the invisible scaffolding upon which all visible structure is built. The cold in cold dark matter denotes particles that move slowly in the early universe, allowing them to clump readily into small halos that then merge into larger ones. This model beautifully explains the large-scale cosmic web. However, some alternative theories propose slightly warm dark matter, where particles have a small thermal velocity that suppresses the formation of the very smallest halos. In a warm dark matter universe, the first galaxies would form slightly later and in more massive halos. As the small-scale power is washed out, the existence of a massive, complex protocluster at Zeta 12, already showing signs of second-generation, metal-enriched stars, placed a severe constraint on such models. The Vance-over density required a prolific population of early, small halos to produce the first stars whose supernovae enriched the gas so quickly. The timeline demanded by the data strongly favored the coldest possible dark matter, reinforcing the standard paradigm, but doing so with a new, empirical check from an earlier epoch than ever before. Hubble's final pre-failure data, therefore, had delivered a constraint on fundamental particle physics from the dawn of time, a silent argument about the nature of the universe's dominant but unseen constituent made by observing the frantic activity of the first visible lights. Simultaneously, the discovery reignited a perennial debate about the very first stars, the mythical population 3 stars. These stars, composed solely of hydrogen and helium, are thought to have been behemoths, hundreds of times the mass of our Sun, burning ferociously bright, and dying in spectacular pair instability supernovae that completely obliterated them, leaving no remnant black hole, only a spray of newly forged heavy elements. No definitive population 3 star has ever been observed. They remain a theoretical construct necessary to explain the early metal enrichment seen in later galaxies. The Vance-over density, with its ALMA detected dust at Zeta 12, presented a tantalizing possibility. Had Webb or Hubble captured the light from the second-generation stars, the ones forming from gas polluted by the first supernovae? Or was there a chance, however slim, that some of the point sources within the glow were actually late-forming population 3 stars, perhaps in a lower mass range that allowed them to survive longer? The spectroscopic signatures of pure hydrogen-helium stars would be distinct, lacking the absorption lines of heavier elements. While Webb's early spectra of individual objects in the overdensity showed clear metal lines, confirming second-generation formation, the theoretical implication was clear. This region had witnessed the complete life cycle of population 3 stars and moved on to the next generation at a breathtaking pace. Hubble's glimpse was not of the very first stars, but of their immediate legacy, the polluted, fertile ground they left behind, already blooming with a more familiar stellar population. It provided the strongest indirect evidence yet for the existence and potency of those first cosmic giants, not by seeing them, but by seeing the profound and rapid changes they wrought on their surroundings. The data was a fossil record of a transformative event that had occurred just a few 100 million years prior, a fossil written in the chemistry of the gas and the pattern of the starlight. Beyond the realms of dark matter and stellar astrophysics, the finding also subtly influenced the search for life's potential cosmic context. If such massive structures could assemble so quickly, then the planets within them, rocky worlds, that would form around later generation stars in these dense cluster environments, would also have an earlier start. The heavy elements necessary for terrestrial planets were present in this region by the time the universe was 500 million years old. This compresses the timeline for potential chemical, and perhaps even biological, evolution in the densest environments of the cosmos. While no one could speculate on the actual existence of life, the discovery underscored that the universe's capacity for creating complex, potentially habitable environments is not a slow, gradual process everywhere. In some special overdense regions, the clock started ticking much earlier, meaning that if life is a possible outcome of planetary evolution, it might have had a multi-billion-year head start in places like the descendant of the Vance overdensity, which by now would have matured into a gargantuan cluster of thousands of galaxies. This was a cosmological perspective on astrobiology, a reminder that life in the universe, if it exists, would not have a single birth date, but a spectrum, with its first emergence potentially tied to these rare early cosmic accelerators. Hubble's last deep look, therefore, touched not just on origins of structure, but on the origins of complexity itself, hinting that the path from the Big Bang to possible biology could be shorter and more diverse than we imagined. The human element of the story, too, reached a quai denouement. The team that had shepherded the data from anomaly to acceptance gradually moved on to other projects, carrying with them the particular rigor and perspective forged in that long period of uncertainty. Dr. Vance, in an invited talk at a major conference, chose not to simply present the science. Instead, she framed it as a case study in scientific resilience. She spoke of the fragility of data streams, the importance of archival whispers, the necessity of multi-wavelength dialogue, and the ethical responsibility that comes with a potential discovery to test it more fiercely than any skeptic would. She highlighted the role of the anonymous peer reviewers who had demanded stronger evidence, and the amateur astronomer whose algorithm had found siblings to their discovery as unsung heroes in the process. The story of what Hubble saw before the data vanished became, in her telling, a parable about the scientific ecosystem itself, an ecosystem that depends on aging infrastructure, human curiosity, methodological skepticism, and technological succession. It was a story that affirmed the value of maintaining and respecting our tools of discovery, for they can gift us insights not just about the cosmos, but about how we come to know it. The telescope's brief vanishment had served as a reminder that our connection to the universe is mediated, precious, and must be tended with care, for the photons arriving at our instruments have been on a journey across eons, and they deserve our most patient and faithful attention. As the years passed, the Vance overdensity settled into its place in the astronomical literature, a calibrated point of light in the ever more detailed chart of cosmic dawn. Hubble continued to operate, its gyroscopes and systems maintained through ingenious engineering workarounds, each observation now a valued bonus in its extended legacy. The story of its pre-failure data became part of the telescope's lore, a tale told to new generations of astronomers about the importance of vigilance, archival depth, and the potential for discovery hidden in every dataset, especially those that arrive on the edge of silence. But the ultimate fate of that ancient, frantic cluster of infant galaxies was a story that could only be told by looking forward, not with telescopes, but with the predictive power of well-tested cosmology. Simulations that had been updated with the precise parameters of the overdensity, its mass, its redshift, its stellar content, could now be fast-forwarded through 13 billion years of virtual cosmic evolution. The result was a stunning projection. The Vance overdensity, that faint glow from the infant universe, would have grown, through unceasing gravitational accretion and mergers, into one of the most massive galaxy clusters in the entire contemporary universe. A behemoth containing perhaps a quadrillion stars, swimming in a sea of dark matter and intra-cluster gas, heated to millions of degrees, sitting at the node of vast cosmic filaments. It would be a dominant feature in its patch of the cosmos, its central galaxy a cannibalistic giant, having consumed hundreds of smaller galaxies over the eons. The light Hubble saw was the first spark of this future titan. This simulation provided a profound sense of continuity, linking the earliest observable moments with the present-day cosmic architecture in a single, unbroken causal chain. The telescope had captured not just an ancient object, but the genesis of a modern cosmic landmark, a before image of a structure that, in the present epoch, might be studied by other means through its X-ray emission, its gravitational lensing signature, or the distorted motion of its galaxies. The data that arrived before the vanishment was a birth announcement for a cluster that still exists today, in a vastly transformed state, a living bridge across 97% of the lifetime of the universe. This forward-looking perspective invites a final, reflective consideration on the nature of observation and time. When we look at the Vance overdensity at Zeta 12, we are not looking at a cluster as it is now. We are looking at it as it was 13.25 billion years ago. In the time it took that light to reach Hubble, the cluster itself has completed nearly the entire history of cosmic evolution, from frantic birth to mature equilibrium. We see only its first cry. This is the fundamental condition of all astronomy. We are always archaeologists, sifting through layered ruins of time, never witnesses to the present state of distant objects. Hubble's final deep field was a particularly deep excavation, reaching the most ancient stratum we can observe with stars. This temporal dissonance between the dynamic, evolved reality of the object and the ancient, fossilized image we receive is the central poetry and frustration of the field. The data that arrived was a message from a universe that no longer exists in that form, a message that took longer to deliver than the entire history of life on Earth. The telescope's brief interruption, its vanishment, was a fleeting moment of static on that immense line of communication, a reminder of both the fragility of our reception and the astonishing fidelity of the transmission across the gulf of space-time. The photons that painted the overdensity on Hubble's detector had outlasted entire galactic lifetimes, had witnessed the rise and fall of countless stellar generations within the cluster they depicted, before finally surrendering their information to a sheet of glass and silicon crafted by a species that did not exist when their journey began. In the end, the legacy of what Hubble saw is not contained in a single paper, or even in the ongoing observations of Webb. It is embedded in the shifted perspective it helped to cement, that the universe's childhood was not a period of uniform, gradual awakening, but a time of dramatic contrasts, with sleepy hinterlands and explosive, Chaotian metropolitan centers. The standard model of cosmology was not overturned, but its story gained texture, depth, and a welcome element of surprise. The findings stood as a benchmark for what is possible when an instrument is pushed to its absolute limits, and as a testament to the fact that the limits are often not in the telescope, but in our imagination and our patience. The Hubble Space Telescope, by staring at a single patch of nothingness for over 100 orbits, revealed a something that challenged timelines and enriched our narrative of cosmic dawn. Its subsequent silence, though temporary, framed that revelation with a stark urgency, transforming a routine dataset into a cosmic telegram marked final transmission. Today, as Hubble continues its graceful aging in orbit and Webb peers even deeper, the field moves forward. New deep fields are being planned for next-generation telescopes on the ground and in space, each hoping to find more such anomalies to map the full population of early overdensities and understand their role in shaping the universe. The quest that began with a few anomalous pixels in a data stream, interrupted by a gyro failure, has blossomed into a sustained investigation into the diversity of cosmic beginnings. And so, the story completes its arc, from a specific, tense moment of technological suspense to a permanent, calm inflection point in science. What Hubble saw before the data vanished was a glimpse of a universe in a hurry, a universe capable of breathtaking speed in its construction of majesty. It was a reminder that the cosmos writes its history in light, and that we, with our temporary mirrors in the void, are slowly, patiently learning to read. The narrative of Hubble's final pre-failure observation and the advance over density does not truly end, for in science, conclusions are merely pauses, moments of consensus before the next question emerges from the data. The integration of this finding into the cosmological canon sparked a quieter, more technical revolution in the methodologies of observational astronomy itself. The process of identifying the overdensity, combining a serendipitous deep stare, archival resurrection, multi-wavelength validation, and machine learning-assisted rediscovery, became a blueprint for a new kind of survey science. Astronomers began designing future Hubble and Webb programs not as isolated, deep probes of single fields, but as coordinated, tiered campaigns. Shallow, wide-area surveys would now be explicitly planned to identify candidate anomalies, which would then be targeted by medium-depth observations for vetting, with only the most compelling targets receiving the precious 100-orbit stares. This strategy, dubbed anomaly hunting or cosmic outlier spectroscopy, acknowledged that the most transformative discoveries might not be the average objects, but the rare extremes that push at the boundaries of models. The advance over density proved that such extremes existed and were physically interpretable, transforming them from statistical nuisances into precious laboratories. This philosophical shift elevated the importance of data mining and anomaly detection algorithms from auxiliary tools to central components of the observational workflow, ensuring that the faint, diffuse, and unusual signals would not be automatically filtered out as noise in the future, but would be flagged, preserved, and investigated as potential windows into extreme physics. This methodological legacy extended to the very infrastructure of data processing. The pipelines at the Space Telescope Science Institute and other major observatories were updated to include more sophisticated low-surface brightness preservation routines. The subtle, extended glow that characterized the advance over density had survived Hubble's standard processing only because of the exceptional depth of the observation. In shallower data, it would have been smoothed away. New algorithms were implemented to protect such features, modeling and subtracting the instrumental and astrophysical background with greater care to avoid subtracting the signal itself. This technical evolution, driven by a single compelling discovery, meant that all future Hubble data and data from other telescopes adopting similar standards would have a higher fidelity for the very faint, diffuse structures that might hold clues to the large-scale gaseous architecture of the universe, the circumgalactic medium, and the faint outskirts of galaxies. In this way, the data that arrived before the vanishment did more than reveal an ancient structure. It helped refine the very lens through which we view all subsequent data, sharpening our vision for the subtle and the extended, teaching our automated systems to see the way a seasoned astronomer might, with a patient eye for the faint whisper against the dark. Concurrently, the theoretical work stimulated by the finding began to bear fruit in unexpected domains. The models of rapid, efficient metal enrichment and secondary star formation within early overdensities were adapted to study the origins of another enigmatic class of objects, the supermassive black holes found at the hearts of galaxies. Some of these behemoths, with masses billions of times that of the Sun, are observed in quasars at redshifts only slightly lower than the advance over density. Their existence so early in the universe presents a severe timing problem. How could they grow so massive so quickly? The fast-track environment of an early protocluster like the Vance system provided a compelling solution. In such a dense, gas-rich environment, the first black hole seeds, perhaps the remnants of the very first population 3 stars, could have experienced rapid, gas-fueled growth, followed by mergers with other seeds, all within a short cosmological window. The same conditions that fostered the rapid star formation and enrichment seen by Hubble and ALMA could also have been the ideal incubator for the rapid genesis of supermassive black holes. Thus, the overdensity became a touchstone in the growing field of early black hole formation, its observed properties providing boundary conditions for simulations that tried to grow billion solar mass black holes by Z to 7. The single observation was now informing two distinct but related cosmic mysteries: the assembly of the largest stellar structures and the birth of the largest gravitational singularities, linking the visible and the dark, the radiant and the utterly invisible, in a single, coherent narrative of accelerated early evolution. On a broader cultural level, the story of the discovery, with its elements of last-minute data, technical failure, and persistent human curiosity, resonated beyond academic circles. It was featured in documentary films and planetarium shows, not merely as a new fact about the universe, but as an archetypal tale of scientific perseverance. The image of the faint red glow, often artistically enhanced, but always labeled as the real data from Hubble's final moments before safe mode, became an icon representing the fragility and the grandeur of the scientific enterprise. It stood for the idea that our understanding of the cosmos is built incrementally, often relying on the durability of machinery in the harshness of space and the dedication of individuals on Earth to piece together stories from digital fragments. For many students entering the field, this narrative demonstrated that discovery is not always a eureka moment at the telescope eyepiece, but more often a grueling, collaborative process of elimination, validation, and intellectual humility, a process that can be sparked by something as mundane as a gyroscope failing and a data stream being interrupted. The human drama embedded in the data, the race against time, the threat of permanent loss, the triumphant recovery and interpretation made the science relatable, grounding the incomprehensible scales of cosmic time and space in a very human story of problem-solving and wonder. As for the Hubble Space Telescope itself, its journey continues, a testament to engineering and human care. Each observation it now conducts is informed by the legacy of discoveries like the Vance overdensity. Every deep field it takes is processed with pipelines that preserve faint light, and every anomalous speck in its data is treated with a little more respect, a little more curiosity, because of what was once found in a similar speck. The telescope, in its silent orbit, is no longer just a collector of photons. It is a participant in an ongoing, multi-generational conversation about the universe. The data that once vanished, then reappeared as a cornerstone of early universe studies, ensured that Hubble's future, however long it may last, would be viewed through the lens of its own profound and unexpected past. The story of what it saw before the vanishment is now permanently woven into its identity, a reminder that even at the edge of its operational life, a great observatory can still point the way to the deepest mysteries, offering one final, deep look that changes everything we thought we knew about the beginning of it all.